Hello, everyone, and welcome to the GeekNarrator podcast. I am your host, Kaivalya, and I am back with another very interesting topic and a special guest today. So, I'm joined by Seeta Somagani from VoltActiveData, which is a low latency stream processing platform that supports very strong guarantees. So, we are going to look at what those guarantees are, what does latency stream processing means, and what are the problems that you can really solve using VoltActiveData. So, Sita, thanks a lot for joining me today. And I'm really excited to talk more about Volt Active Data and about its features, about its architecture. Let's start with a little bit of introduction about yourself and what you do at Volt Active Data.
Thanks for having me on your show, Kaivalya. So, Seeta Somagani, I'm a solution architect here at Volt. I've been with Volt for a little more than 8 years now. I got my education in computer science, and I worked as a product engineer, and then as an engineer in professional services, and then I slowly moved to pre-sales. A little bit more exciting part of the professional services job. So I've been with Volt, and my day to day is I speak with prospects and customers and help them either in designing solutions with Volt or making sure they're getting the best out of Volt for their applications.
Awesome. And I would like to understand when we talk a little bit more into depth, like what are customers using Volt Active Data for, right? Like, what are their problems? So,
Mhm.
really excited to do that. As with any other system that we want to talk about, I really want to start with the historical context, like why something was created.
Mhm.
And so let's do that. And I know a little bit about the history, how it was called VoltDB, and it was sort of rebranded into Volt Active Data. So also share a bit about that thought process and what was the idea behind this rebranding and how it all started.
Yeah, sure. So, started in 2009 by Dr. Michael Stonebreaker. He is the Turing Award winner behind lots of data products. So, initially, he wrote the white paper of OLTP through the looking glass, where he identified what are the challenges with the traditional databases, the databases of back then, which were being used for any place where you had data to be persisted and processed. You were just going with the big databases. So he found out that most of the processing time is being spent on the overhead rather than the actual workload itself. So Stonebreaker then he wrote this other paper, HStore, which is a horizontally scalable a transactional engine. And HStore essentially is a rethinking of the database of a transactional OLTP database by you have all of your data in memory. Now the RAMs are, RAM size is increasing, it's getting cheaper. So some of this workload can reside entirely in the main memory. And your transactional workload is also pre-planned. You're not running analytical queries. There's a different product for that. That was based on a C-Store paper, which was Vertica. So in 2009, Volt was actually spun out of Vertica based on the HStore paper, or called VoltDB back then. So this was the horizontally scalable transactional counterpart to Vertica, which was horizontally scalable analytical database. So over the time, there were some core design decisions which were made, all explained in the HStore paper. But over time, we have seen the market evolve, and our let's say the need to educate the prospects and educate the wider industry has also evolved. When we say database, there is a certain connotation that used to come with the database, as in here's a place where you would store the data and then you retrieve it when you need it. And the complexity is more in the retrieval. How complex can your queries be? How quickly can your queries run and retrieve your data, rather than thinking about a more scalable approach to the problem, as in we treat the data as an unbounded set and we process the data as it's coming in. So streaming was more of an essence for Volt in the beginning, and we wanted to make sure our messaging in the market was clear. So we have implemented a lot of streaming semantics like Kafka API and stream processing semantics. So we then rebranded to Volt Active Data. From VoltDB, we moved to Volt Active Data. Also, around the time we moved into an entirely commercial model. So Volt Active Data, the reason behind the name is that we want you to uh, get the best out of your data. So data has this active life, and the amount of value you can get out of it rapidly goes down. So at the ingestion time or at the beginning of this event, there's a lot of value that you can extract out of it, as in you just hung up your phone call, and what offer can the operator give you because you just hung up your phone call? Maybe it was due to a bad connection, or maybe it was due to, hey, I'm running low on my balance. So that's a very small window of time before you hang up the phone call and put the phone in your pocket. You need an SMS, an offer to be made, or in the case of fraud detection, for example. So it's that active data, that's what we operate on. So Volt Active Data was the brand that we changed to, and we're continuing down that path and working more with streaming use cases, uh, having the strength, the solid core of an in-memory transactional database.
Very interesting. Um, so is it only about the real-time data that is coming in? So when we talk about, you mentioned unbounded stream of data, right?
Mhm.
And that mentions a lot about the volume of data and the velocity of data, and it's pretty high in these systems. Even if these are like transactional system, these are not traditional transactional system, but these are really modern transactional system where there
Yes.
are like hundreds and thousands of transactions happening per second. um, so you mentioned about the active data part, right? You also mentioned about fraud detection and use cases like that. So is it also about the understanding of the historical context of data, or only making decisions in the real time?
So it's processing the events in real time. So low latency is important for our customers,
Hmm.
whether it's making an offer or detecting and preventing fraud. But you can make a use of historical or whatever analytics you have. So Volt is built to function in that way. So we're not trying to be both a transactional database and an analytical database, but doing the transactional part very well.
Okay.
And you push the events out after they've been processed initially out into an OLAP or whichever your system is, and then you can ingest that back into Volt, because it's, at the end of the day, it has the relational semantics. You can create tables that you can do joins on, so your streams can be joined with the existing tables. Maybe those tables have some thresholds where, if it exceeds so many transactions per hour, maybe you would call that a fraud.
Okay, interesting. And I guess the in-memory part is important because we are talking about low latency here, right? Before we actually understand how all that works, and now I'm more curious, um, let's try to also define the problem statement. Like, what are the typical problems that people usually face with these kind of systems that are highly concurrent and tons of transactions happening and high velocity of data coming in? So,
Oh
what are
yeah.
these common challenges that you have seen your customers face?
Yeah. So we've been around for 14 years, so our use cases are very diverse. But I guess, the biggest use case for Volt is in the telecom industry. So charging for a mobile operator is a very important and something that's has a critical nature, right? If you're not charging your customers, then you're losing money. That's especially true in prepaid markets like in India and Asia and Africa. So charging tens of millions of subscribers and their utilization of their data and their calls, that results in hundreds of thousands of transactions per second. So the database, essentially, some customers use Volt as the database, as the operation data store for maintaining your balance, what your balance is, and making sure that the operator doesn't have to eat up the cost in case of loss of any consistency.
Hmm.
Even if there is a family plan, making sure that the entire family is sharing the same balance, and you are able to hold that accurate balance and bill the user appropriately. So charging and applying policy. So in couple of years ago, some years ago, we used to have an operator would come out with the scheme saying, well, if you switch to T-Mobile, then I'll give you Netflix for free. That used to be the case in the US. So the policy can get pretty complicated. Like, what is your data utilization on? How do we rate it, and how do we accrue it, and then you have to bill it at the end of the day, and how do you even mediate different streams of data that's coming in,
Hmm.
and produce the CDRs at the end. So telecom is one of the biggest users of Volt, and we have a lot of deployments all across the world, here in the US, Europe, India, and Southeast Asia and Africa. But the other common use case are like in gaming. Dream 11 was actually the largest fantasy sports application, the platform in the world. They have the last IPL season, they actually exceeded 200 million active users. And Unity 3D also is, they have about 4 billion users. But the workload is kind of different, because for Dream 11, it all gets compressed into this half an hour after the toss and before the match begins. For Unity, it's more spread out. So they both deal with high volumes of data that they need to keep accurate and processed with exactly one semantics. And we have customers in other industries like financial services as well. But these are the top and more interesting use cases.
Yeah, very interesting. So, yeah, as it's pretty clear from your examples that low latency is one of the most important aspect. And then
Yeah.
you also mentioned on correctness. You mentioned like things like exactly once, and you absolutely want to count the data or track the data usage accurately. Otherwise, it's going to be a trouble for the customers. So we'll get into that a bit, how all that works. So when it comes to high scale, right, and concurrent access, uh, there's of course some other issues like latency spike or sudden traffic spikes that, let's say there's a special day or some sort of event that is happening, as you also mentioned Dream 11. So
Mhm.
there are spikes involved and all of that. So is that also like a common use case that people end up using something like VoltActiveData?
Yeah, so the variance in the workload is something that our customers have to deal with. Honestly speaking, the most of customers till today have, they just plan for it. They don't rely on having to auto scale the database cluster, because it's still stateful system, and scaling it can be a little bit of a
Yeah.
challenging. But Volt does support auto scale out and scale in, whether you want to use it on Kubernetes or on virtual machines. So you can do that. It's a no hassle operation. But yeah, mainly customers, they estimate this is what I would need for the IPL, and after IPL, Dream 11 then just scales back down to a lower level.
Interesting. Let's talk a little bit about the high level architecture. So when I look at Volt Active Data,
Hmm.
you know, what are the components that I am looking at, and what are the key features these components are used for?
Yeah. So this is all. There are a number of products in this space, right? And some of these products are built on other products, like maybe Flink, or the underlying they use other open source product. But the entire Volt Active Data, it's built on. It's our custom software. Most of it was built on the HStore paper, at least the core of it, right?
Yeah.
So at its core, it's a transactional database. So if we look at the transactional database and even look at its own core, there is an execution engine at the heart of everything. The execution engine is able to do some operations on tables, like the relational semantics that you would expect. Tables, views, streams is something that we added. Also, kind of in a relational model, stream looks like a table, but it doesn't actually hold any data. You write to it, it ends up somewhere else. It ends up in a buffer. So these relational objects are all supported by the execution engine, and the execution engine, it will take a SQL fragment and it will execute on the memory that it's managing, the tables and views that it's managing, and return you the results or make changes or whatever needs to be done. So at its core, it's relational, and it's written in C++. So it's, you're not worried about your Java heap space and garbage collection and things like that. So this is a model that is built to be very efficient and scalable. Now we take that and we scale it by the cores that you may have on your machine. So you would take Volt, and then the first thing you would do is partition it. How many sites would you like to deploy in your Volt? So let's say you have a 8 core machine, maybe you would pick, I can do like 6 sites per host or 8 sites per host. So each of those sites would have a Java thread, which is responsible for executing the transactions. So the Java thread will accept, which is the site, it will accept the incoming requests and treat each request as a transaction, execute it with the execution engine, and then give you back the response. So the semantics, the ACID semantics, are all implemented by the site. Now Volt, so we go through the ACID properties, right? So Volt does not have client-side control. So the stored procedure invocation is the atomic unit. So to be scalable, you cannot have a client open a connection, do some operations, and wait for the client to then commit. So the stored procedure invocation are atomic. So you issue an invocation and then you wait for the response, and that's it. So that allows us to keep all the code with the data itself, and that will be the most performant way. And the consistency, we make sure that the data ends up in a consistent fashion. That's the purpose of the execution engine. For durability, every single invocation, the stored procedure invocation that comes in, is logged to a command log so that you can uh, rerun the command log and restore your state to the previous state. So it's all durable. You can also capture snapshots so that you can cut down on how many commands you have to run. And the most interesting thing about ACID is the isolation part. So Volt implements strong serializable isolation. So if you just look at other data technologies, strong serializability, even if they provide, it's not something that is enabled by default. In Volt, it is the only isolation level that is available, because Volt, it's not just to provide a feature for the end use case. It's also important for how Volt does its replication. So you are getting these stored procedure invocations, you're running them, you put them in a queue, and the invocations are picked up from the queue and executed by the execution engine, and the response is sent back in an asynchronous way. So we depend on determinism to do the replication. Now, if you have multiple copies of your partitions, right, for high availability, you would want multiple copies, one or two or more. And you can simply do that by specifying the K factor when you start up Volt. So when you start up Volt, you say, here's how many sites I want per host. That's the parallelism. And here's how many copies I want to make on the data. Now Volt will figure out, okay, how am I going to distribute these partitions? How am I going to distribute these replicas and the leadership among them, so that I have a more uniform distribution of the workload, and also I can guarantee high availability. So when a stored procedure invocation arrives at the leader partition, let's say, so what we are depending on is that if you start from the same state, if the replicas, all of the replicas are starting from the same state, and they are running these operations which are deterministic. So running the operation from that state is going to result in the same end state. And the operations are all ordered in the same exact order. Then we don't have to do additional coordination to ensure the replicas are all in sync, that there is no divergence between the state of the replicas. So it's that fact that Volt relies on to provide the replication, which also then extends out to the use case. So in your use case also, you're relying on the fact that our customers rely that you get strict ordering per partition, and you can do exactly once processing of your transactions. So it's that the core execution engine, and then the site which envelopes that execution engine to provide the ACID semantics.
Interesting. I have many questions there,
Please.
just to clarify my understanding. So to start with, the core execution engine, and that stores the data in memory, right? And you mentioned for durability you use command log, uh,
Mhm.
and but these commands and the stored procedures that are run, these are the same things or these are different things?
Yeah, so the stored procedure is actually running in the site.
Okay.
So stored procedure you write using Java. So
Yeah.
that's the language for
Yeah.
us. You write using Java, and interspersed in your imperative logic of Java, there are SQL statements. So the actual modification to the data is done through SQL, which is what the execution engine runs. The Java logic is running in the site. It says, well, first check this table and get me this value. Okay, and in your Java, you can write, you can clearly express if the value that I just got from this table is this, then go do this update or then go do the other update. So that's the stored procedure. So the client is sending a stored procedure invocation. Invoke this stored procedure, which can be accessing however many tables that it wants,
Hmm.
right? So invoke this stored procedure with these parameters. So that invocation itself is written to the command log. So the command log is just a redo log, which starts off from the base of a snapshot of the data. So if we captured the snapshot at 12 p.m., all the commands that were run after 12 p.m. Would then be the command log. And if you need to restore it, you restore the snapshot that was captured and then rerun the command log to get back to the latest state.
Okay. And these, the stored procedure, that the Java stored procedures, uh, these are the queries that are running on data, or these are also, these are mostly on the query, like the read side of the things, right?
It's both
It's both.
read and write.
Okay.
So this is the model that works better in streaming, right? So let's say the events coming in are, take the case of a mobile charging. Here's an event that's coming in. Just said 10 seconds of talk has
Hmm.
happened on this mobile number, on this plan, and whatever other details there are. Then in the stored procedure, then you can check, hey, does he hey have the balance, or should I tell them that, hey, there's no more balance, you have to terminate this phone call, or we rate this utilization with a certain rating, and then we deduct this 10 minutes from the reservation on the balance that we had made. So all of this is happening on the ingestion side. So it's a combination of read, write, all whatever processing you need to do, even windowing if you need to do something for fraud. All of this is happening on the ingestion on the right side, lesser the read side. But everything, the stored procedure is the only unit
Okay.
of work that Volt recognizes that keeps things simple and performant for us.
Interesting. Let me take an example here just to make things a little bit more clearer, at least in my head. So, since you're taking some examples from telecom, I also worked on a similar problem. Uh, so, there are these, the scooters like Lime scooters and Uber scooters, and there's a ton of them in Berlin at least. And they have a SIM card in them, right? And there
Yep.
are companies that have like thousands and thousands of scooters, and again, I'll use the same example of data usage tracking. So let's say I'm the company owner and I have these scooters laid out across the globe, many different cities. And what I want to do is I want to track the usage for each of these SIM cards and bill my the users of these scooters accordingly, like how
Hmm.
long did they go and what was the data usage. Maybe they can also use some other type of device or something like that.
Yep.
And I want to track the usage data, charge them accordingly, and I want to use Volt Active Data System for that. Uh, so, what is happening? Like, where does it fit in my architecture, and what kind of data am I ingesting, and what kind of queries I'm writing to understand what's happening?
Yeah. So whatever your favorite language is, we might have a client library for it. Let's say Golang or Python or Java. So you'd use the client to send, or you can use the Kafka API. So we
Okay,
support Kafka API as well, and the client doesn't know any better. You can simply point a Kafka publisher at Volt and say, "Here's a Kafka broker. Just send these events." If you want a request response, then you might use a Volt client. So the events, whether it's events coming in or whether those are client calls that are coming in, everything is a stored procedure invocation. So the stored procedure you would write. So your application logic kind of lives between your application server, which is somewhat lighter now, and the heavy lifting is done on Volt itself. There you would implement the business rules. If it is maybe there are different kinds of scooters. If it is this kind of scooter, this is the charging rate that you have to go, and you would create that policy tables. Let's say upfront, you will create those policy tables as these events are coming in. You decide, okay, here's an event, here's a usage event, right? On with these parameters, I can join with that existing table. I'm going to make that a replicated table, not a partition table. I want to make that a replicated table. So it's because it's mostly read only and it's shared by all the different partitions. And I'm going to partition the events table. Let's say I want to hold the events for some window of time, let's say 1 day. You can create a table with a TTL on it, and you will keep the events for 1 day. It's going to be sliding for 1 day at a time, or continuously sliding. And the events can then be inserted into that table. You join it, you insert it just for persistence, and then you decide, okay, this is the value that must be charged. Maybe I would like to now export this event out. Now here's a chargeable event, okay? And you can write out to an export destination, and that destination can again be Kafka, or it can be a JDBC and it's a JDBC database, or it can just be a REST call as well. So you are ingesting from your application or from Kafka or your Kafka publisher, processing it using the state that you are holding locally and the state that you have uncontested access to, right? There's no waiting for a thread to free up. It's just because it's a serializable isolation, your thread, your stored procedure has access to that data. You use that state, you process it, and then you export out an event. So it's that streaming pipeline you can build using our clients, the Kafka API, and our export subsystem.
Okay. Now I think it makes sense. And so the idea of this stored procedure is to basically have sort of this atomic blocks of code that can be run uh, as you called command, right? That's the command, and that is run on certain piece of data, and then that can be used for inserting or even based on some rules or reading those data.
Yes.
And you also mentioned that this stored procedure can span across different partition of data, right? Like, or is a stored procedure bound to query data for a single partition only?
So you have both,
Okay.
but the one which is working inside a single partition is obviously going to be a lot more performant
Yeah.
than the ones that go across. So you do have such workload, and we support that with what we call a multi-partition procedure.
Interesting. And then the ACID that we talked about, is it also applicable for these kind of queries where it talks to like multiple partitions?
Yes, yes.
Okay.
Yeah, regardless of what question you're asking, Volt, and however many copies of data you have, it is always going to be strict serializable isolation. So you have the best consistency level.
Okay.
And this is only possible if the database engine itself supports strong ACID semantics, but also in a distributed system fashion. We support strong correctness guarantees. And we are tested by Jepson, Kyle Kingsbury, tested Volt. And yeah, recently we were only testing like the core of Volt, just the transaction processing. And recently we have extended this Jepson testing out to our export subsystem as well. So that for sure, if you are getting let's say some IDs or some records being exported out to your Kafka, the guarantees extend out to that export of data as well, not just to the processing but also to the export.
Oh, interesting. That does make sense. Uh, I want to understand a bit more on the partitioning side, right? Like typically, let's say in other systems, I want to define, oh, this is my partition key or something like that, and based on the data, and I try to make those decisions in such a way that there are no chances of hot partitions. And so, what are some of the recommendations given to avoid such situation with Volt Active data? Given that it's like in memory database, so primary, like most of the data is in memory, I believe, and that
Yeah.
so that makes it even, I guess, important to not have these hot partitions. So what do you have to recommend there?
Yeah. So, yeah, our customers, they do have this question like, how do we partition our data? And you can combine more than one column to create a partitioning key. That gives some flexibility to some customers, but it is essentially a peer-to-peer shared nothing kind of an architecture. So every partition is given the same amount of resources. The resources are divided exactly among all the partitions. So it does depend on a good data schema design, understanding the workload. And sometimes what that means is you have to maybe like divide your workload in different ways. So we have this financial services customer, major bank, and they use Volt for monitoring their risk exposure. And it happens that you would like to process the data first along one dimension and then process it along another dimension, which is common in stream processing, right? This is all still strongly stateful stream processing. So what they have built is ingest on one dimension, partition on one dimension, and then they use our exporter to send a request back into Volt to now process on another dimension. So they repartition the data. So there are some things that you can do, but always we always emphasize the importance of good data schema design, understanding your workload, and then taking the right decisions there.
Okay. I think it depends on the distribution of your traffic, and then it depends on your schema, what kind of queries you want to run. It's not always easy to answer like, oh, this has to be your partition key. But of course, there
Yeah.
are some good properties of your partition key such that it doesn't end up in a hot partition. And
Yeah.
I'm also curious on the determinism part you mentioned. So you mentioned that these stored procedures are also stored on a command log, and whenever you execute these stored procedures, no matter what replica you're running those commands against, it has to be deterministic, which means it has to result into one value, which is equal.
Yes.
Uh, how is that ensured?
Yeah, so it's we provide the stored procedure environment so that it just depends on your code, the code that you write. So access to any functions that Volt provides, like the function to get the current time or function to get any access to any data, any table data, it's all ensured that it's all consistent. So you make a request to get time or get a unique ID or something like that, all the replicas will get the same time and the same unique ID. So we provide the facility to make a consistent or a stored procedure deterministic.
Hmm. And this is so powerful, actually, when you have to replay the log, right? Otherwise, let's say you're generating a unique ID and it's not deterministic. Let's say for each invocation of that command, it is creating a new ID or something or getting a new timestamp. It might just break the system depending on the logic. So is it that, let's say I have a like a side effecting function like creation of unique ID, is that already stored? Is that invocation already stored somewhere? And how is that determinism provided actually?
So we just provide these functions, right?
Ah,
So
okay.
you want a unique transaction ID or a unique or current time.
Okay.
Inside a stored procedure is simply it's an extension of a Volt procedure,
Okay.
and that function will ensure that it is deterministic.
Okay.
I mean, you can go ahead and try to make it non-deterministic by getting system.nanos,
Yeah.
right? And you will break it.
Okay.
It's up to the developer, but Volt provides all the facilities to keep it deterministic.
I see. I see. Okay. So there are some functions that are provided by Volt, and it's best to use those functions instead of regular Java functions to make it
Yeah,
more
yeah,
deterministic. Okay. That does make sense. Cool.
yeah,
And I mean, that was my next question, but I guess you already answered. Like, since I'm writing Java code, I can
yeah,
do like tons of different things. I can make a service call or something like inside stored procedure. So,
yeah.
what kind of sort of restrictions I have when I'm writing these stored procedures?
Yeah, that's a very good question. And because it's strong, strict serializable isolation, right? If you have one procedure which takes 1 second, that is going to impact the rest of the procedure calls.
Yeah.
So you want to make sure the design guideline is that you want to make sure it is doing one single chunk of work. I mean, believe this is for transactions, right? So we're focused on running transactions. So the workload, you
Yeah.
want to make sure it runs as quickly as possible. You use the data, you use the state, You run your logic and quickly get out. But customers have more complex requirements. So what we have for such requirements is something called a non-transactional procedure. We call it a compound procedure. Now, compound procedure also allows us to build some sort of a DAG inside of Vault. So compound procedure can invoke multiple stored procedures. I mean, each stored procedure itself is transactional, but the compound procedure itself is not. It has its own thread pool where it is scheduled, where those calls are scheduled and answered. So that compound procedure can invoke multiple parallel requests and then wait for all of those requests to come back. It can be a service call, or it can be any logic that you feel belongs to be running on Volt itself. But most typically, it's a bunch of stored procedure calls. I was during the initial development, I was part of this, and I was testing this out using a recursive procedure call. So I would just issue like, here's a field team organization. I want to make sure I want to get what the overall revenue per region, right? It's a recursive call.
Yeah.
So you can do such things as well, but the developer has to really understand, hey, this is a transactional system that is built for running these things really quickly. But if you want a little bit of additional features, somewhat that doesn't have to be transactional, some workload, you have the option to do that as well.
Okay, pretty cool. Um, and let's say I write the stored procedure, and I might have some bugs, right? Like, let's say an infinite loop or something. I'm just guessing here. Maybe
Yeah,
that's
yeah.
not allowed. And so, is there some sort of timeout that happens when these stored procedures are executed, so it just doesn't block the entire partition or something?
Yeah, I mean, deployed on like Vodafones of the world, there's a lot of these things will
Yeah,
come into. Uh, so yeah, there's a unit testing framework. It's a Java class, right? So you can unit test it. But yeah, you can also set some of these boundaries. So you can set a timeout for each procedure. You can set timeout for, let's say you want to make sure that you handle network disruptions also properly. You can set a timeout for your heartbeat as well. So there's those boundaries that you can set.
interesting. Cool. Let's talk a little bit about the fault tolerance part of the system, right?
Sure.
Like that. Uh, so, of course, failures happens, machines go down. What happens when this partition goes down or something? What happens to the data?
Yeah. So, yeah, the K factor is at the design time, you decide, hey, what's the K factor that I would need based on your uptime requirement? What is the uptime requirement for your service? And what is the uptime that I am being provided at a machine level and at a data center level? So, can I get more uptime by designing a good enough solution? So, you come to the table with those numbers, right? And you can then the factors that the variables that we're trying to get at is what's the K factor that you need. So Dream 11, what they do is they use the K factor and they replicate across multiple availability zones as well. So you can choose to have the ability to survive against the loss of single node or an entire availability zone or even entire region. But within a single cluster, the K factor works. It allows you to say lose one node, two nodes, three nodes. You can build yourself up against that. Availability zone, across availability zones, you can spread out your cluster so that you can survive the loss of any one AZ. But regions, then, because this is all synchronous replication between the replicas in Volt, but going again across regions will then become prohibitively expensive because the network lag is going to be high. So then you can use asynchronous replication between the different clusters. The asynchronous replication will then bring consistency questions up. So we have a conflict resolution and a conflict logging mechanism. So any conflict that happens on the same key on the same row ID, two different updates are happening. I mean, we try to resolve some when we can, like a delete comes in after an update. Yeah, you ignore or the other way around, you can ignore one.
Yeah,
But when those cannot be ignored, we write those out to, if you choose a Kafka topic and say, here's all the conflicts that have happened, you decide what to do on this. So yeah, our customers, pretty much all of them, they need the service to be running all the time. They need high availability, use K factor, and we have internal optimizations to survive the loss of more than the k factor nodes, distribute across different AZs that has been battle tested under heavy workloads, and also deploy across different regions. And our telco customers, actually, we went live with one customer distributed across three nodes, three different regions. So we can do three or more regions as well.
Okay, that's interesting. So a little bit of control is also on the customer side, like how much availability they want. And depending
Yeah.
on that, they can set this K factor and get the required set of availability, right?
Oh yeah. I mean, there's a trade-offs to be
Yeah.
made, right? It's not something. There's a sure shot solution. It's gonna affect your performance. It's gonna affect your consistency.
Awesome. Yeah. Uh, that makes a lot of sense, right? And uh, since we have talked a little bit on the use cases, let's also talk about some of the. So you already mentioned like Dream 11 and some examples from telecom and also some finance examples.
Mhm.
Uh, what are some other use cases where Volt Active Data would really shine with its features?
Yeah. So 5G was supposed to be here and bring us this crazy new world of innovations. Hasn't happened, but we're speaking with customers who are, I mean, I wouldn't call them customers, like partners and other players in the 5G who are playing in the 5G arena. Like, how can we solve some practical challenges with the low latency that 5G can give you, the low latency and high throughput and all of those brilliant things. Mostly these are around IoT. We were talking to some potential partners, like even Verizon and the big network operators. They want to like expand out now to more have more devices on their network, right? Like on the private 5G network.
Yeah.
So, what can enable adoption of private 5G networks is you have devices that can do their jobs in an automated fashion. They don't need a lot of processing on board so that you can deploy a ton of them, right? So, being able to do the control of these automated devices and whose functioning has real world, real life consequences, I think that's a really good use case for Volt. We're able to ingest events from massive number of devices, massive number of events, take decisions in the context with consistency. So that essentially becomes an extension of the onboard computing with the low latency, right? With the low latency, you're able to say, just offload this data processing and this data state persistence to something which is on the, let's say, the factory floor, and is able to help us out with taking these decisions so that two robots don't run into each other, or they don't run into a human, and they are able to share the work in a more optimal fashion than being given this plan of work ahead of time and they go and they do it. So the IoT and the autonomous devices, I think, holds a lot of promise for a technology like ours, which is built to do both scale without compromising on consistency.
Awesome. Yeah. Um, let's talk a bit about the future. You mentioned 5G was supposed to happen but didn't happen. So in a way, that's also future. But I want to talk a little bit more from the high level perspective where the streaming world is going. So
Hmm.
you mentioned it was called VoltDB, and then you rebranded to Volt Active Data, and that speaks a lot about your strategy. Uh, but what's in the future? Like, what are some new use cases or new type of customers that are going to have this streaming use cases, and how Volt Active Data could help them?
I mean, it's both new use cases and also the existing ones that are moving into streaming these days, right? There's we're working with more devices than with people, so there's data flowing in. So even from our telco customer point of view, they are also talking about, hey, we were thinking in terms of OLTP and OLAP, like how do we fit this new pattern or this new paradigm of stream processing in? So we're working with our existing telco partners with that. And I think the industry has also matured in the last decade, Kafka being the big disruptor and bringing the stream the streaming idea into mainstream by allowing us to decouple the different services, rely on this central event persistence for us to decouple and then bring the publish subscribe semantics. And people have started to build more on top, sometimes with off the shelf and easy to use and open source solutions. But we are seeing that the challenges remain when there is so much decoupling between like your state and your stream persistence. And the processing has to bring these two together, and doing that in real time, and being able to provide a queryable state. These are all challenges that we hear that a lot of people are going through.
Yeah.
So the streaming databases, I think, is a newer categorization in this market that's coming up recently, and we believe that that's um, important way to solve these challenges. Being able to do provide the streaming semantics at the same time, have an associated state persistence that is also queryable. I think we can add Volt can add our own flavor to it by focusing on the transactional side. You have streaming analytics, you have operational data warehouses who are also like streaming first. But here is Volt, which can work as a transactional streaming database, if I can put it that way. So that's kind of the direction that we are looking at, and both guided by our strengths and also the trends that we are seeing in the market and with our existing customers.
Awesome. Yeah. I mean, some of the problems that you mentioned when your data is somewhere else, but you want to do stream processing somewhere else, latency is a huge problem there because first you have to take the data out of your database and put it somewhere and do stream processing there. And so, yeah, I'm excited to see what's in the future. And but it was amazing to understand how Volt Active Data works and what are the problems that it can be used to solve. And it's an interesting mix of the transactional world and the streaming world. uh,
Exactly.
so very cool, and thanks a lot for sharing those insights with us today. If folks want to know more, our viewers, what should they look up to?
We have, well, we have our LinkedIn page, we have our web page, voltactivedata.com, and you can send a message in the chat and that sends it to us. So, yeah, or you can reach out to me directly on LinkedIn. Yeah, there's many ways to reach us. Just find us on Twitter as well.
Awesome.
Yeah, so it was great speaking with you, Kaivalya.
Awesome.
Very
Yeah.
engaging conversation.
Thanks a lot. And for our viewers, if you are more interested into your use case and how Volt Active Data can help you, do check out the website and do reach out to Sita for that, and we should be able to share more information. So
Absolutely.
thanks again. For viewers, if you like this episode, please don't forget to like, share, and subscribe. So thanks a lot.
Thanks, Kaivalya. Take care.